Okay, so it's lesson 6. It's MDEV1001, and we're just kind of looking at mobile data structures. We played around a little bit with Firebase in your Android course, but we're looking at some of our other options of how we kind of can store and move data around. So for those of you who I gave a number 1 to, what I'll do is, these slides are online. I'll give you the link in a minute, but I'll take some notes in here as well, and then I'll publish the updated ones at the end of the class for you as well. Okay, so if you had a number 1, what did you find out? What are some of the ways we could store data in a mobile app? Oh. SQLite? Yep, so that's a really popular local storage simple database. Sorry, shared, I couldn't hear the second word. Yep. Okay. All right. So what are some of how would you make this decision, right? It's quite a few options. How are you going to decide if we're building an app, which one of these options makes sense for your app? What kinds of questions would you think about in deciding which of these you're going to use? So we have all these options, and you've been asked to build an app, and that app is going to involve storing some data. We just listed 5 good options. How are you going to decide where your app is going to store data? I mean, okay. So yes, so what would be some of the decisions? You're right, the answer is it depends. So it depends on what? Okay, good question, right? Can the app be used offline? If the answer is yes, it needs to be used offline. Well, which of these are options and which of these are not such good options? Yeah, so disk, shared, and device memory, then that really lives on the device itself, right? We can be on a plane, we have access to our data. So that seems kind of convenient, right? So why would we ever look at options? Well, and actually, where does SQLite live? SQLite is kind of a hybrid, actually. SQLite supports local storage on the device, but it also supports cloud service. Okay, so we can have both. What are the benefits of using storage outside of your device? Why would you ever want to store data off the device itself? Okay, that's number 1, right? You know, I log into to Spotify on my phone, but then I want to be able to log in later on my computer, right? So I can share if that data is not dependent on my device, right? I can play a song here, interrupt it, go on my computer, and it picks up exactly where I left off. So sharing is one good reason. Why else would we maybe want to store? Right, okay, if the data lives on my device, what happens when I drop the device? I get pushed in the swimming pool with the device in my pocket, right? Where's my data? Right, it's gone if it's on the device. Okay, yep, can you explain a bit more? Absolutely, really good point, right? We've got limited storage capacity on our devices. Whereas if we're going to store that data on a cloud server, well, no problem. We can add as much as we want. We're not eating up memory space on our device. What about from a performance perspective? We're thinking about performance. Where would we want to store data? Probably locally. Why? Yeah, it's simply going to be faster to interact with the data, to retrieve it, display it, update it, add to it if we're storing it on the device itself. So these are all, there's no right and no wrong. It really does come down to, it depends, right? What are we building? What's the use case? What does the data look like? What's the vision for the business of this app that maybe we're creating on our own or our clients asking us to build? So we need a data storage strategy that makes sense for this, because it can be difficult to go ahead and change this after the fact. If we plan on local storage, thinking, oh, this is just going to be a simple 1 or 2 activity app, and then suddenly we have 10,000 downloads a day in the App Store, well, local storage is going to be a problem. So it is a balancing act that we're trying to figure out. All right. What about for those of you who had number 2, what's a NoSQL database? What could you tell the number 1, 3s, and 4s about NoSQL? Okay. All right, so that's one of the big keys. NoSQL databases are schemaless. So if you think about everything you've ever learned about relational databases and how we design them, probably the very first thing you ever learned was how to build a database schema, right? What is a table? What is a column? What is a key? What is a relationship? All of that stuff, all that knowledge, kind of, we put it over here when we're working with NoSQL. It's a completely different way of working with data. So we have no schema. It's non-relational. So if it's non-relational, how would we handle relational data? Just for context, let me ask, how many of you have, I'm trying to identify an app that we probably all have on our mobile devices. Who has an app for ordering food from a restaurant, like a Skip the Dishes, that type of app? You? Who has a music app like Spotify? Okay. All right. Well, let's think of, we'll maybe use that context of ordering food on an app. Okay. So if we're going to make an order, we want to be able to order a meal and have it delivered to us. If we think about that in a relational database kind of way, what would that database structure look like? In a simple term, if we had a simple app that would allow somebody to order food, what would the tables be we would need? Okay, so we'd have an order table. Yep. Yeah, so we might have a separate address table, right? So maybe as a customer, I want to feed my poor class who lost their regular instructor. So rather than having pizza delivered to my home tonight, I'm going to have sushi delivered to you guys today. Right? So we may have a relationship here. And then there's at least one other important table. Like even this is a really simple app. There's one other important table we're missing. Yeah, the actual items or the food or the products, right? With these 6 tables, we could probably build an app similar to like a Skip the Dishes kind of app, right? I can create an account. I can choose a restaurant. I can see the list of products they make. I can make an order, and we'd probably have a junction table here because this would be, and then I also could have an address book so that I can order to different addresses. That's the basic outline. And we would have, we'd have a series of keys that would allow us to join, one restaurant has many items, one item can appear on many orders. One customer can make many orders. One customer can have many addresses in their address book. That's the basic schema. And obviously we could flesh out, I won't flesh out what the columns look like, but you guys are in a graduate program. It's probably not too new to anybody here in this course, I assume. A NoSQL database, it breaks all this stuff. We don't have to have this rigid schema. So in a relational database, we have tables, columns, and records. We even have different terminology in a NoSQL database. Instead of tables, we have, you mentioned, documents. Instead of tables, we have collections. Instead of records, we have documents. And in a relational database, our data, if I want to order something, right, my data is broken up among all these tables. My customer information is here. Information about my order, the total, the order number, the date is here. Information about the products is here. Information about what restaurant I ordered from is here. So all these things are kind of scattered throughout the database. In a NoSQL database, it would look totally different. I basically have one document. This is actually a single document and everything gets nested inside of it. Now that does mean we may have repetition, unlike here, right? We might be repeating the item name in every order. But everything lives together. So we don't need joins, we don't need keys, we don't need SQL queries. And we don't even need a schema. We don't need to say, this is what an order looks like, this is what a customer looks like. We don't care. So for example, my customer profile, I put in my name and an email address. Your customer profile, you put in a name and a phone number. We can both be customers, but our customer information can look different. That's okay, it's allowed. So, as I said, it kind of breaks a lot of the rules. Why would we want to do this? We spent a lot of time. The relational database isn't going away. This isn't going to replace it entirely, but we now have another option. Why might we want to store our data, particularly in the context of a mobile app? What's some of the benefits of that version as opposed to our traditional version? Okay, that's right. Can you explain a bit more why that is? Okay. So number one, we tend to use NoSQL databases when we're dealing with large volumes of data. So we want it to scale. Right? Think about how many orders go into an app like Skip the Dishes into their database around the world every day, probably in the millions, right? Every single day. So it's highly available. It's simple to retrieve because everything lives here. We don't need a complex query to show one order. We can just go grab that one object and it's got everything. So scalability is a big one. What would be the other, coming back to your, it depends which one of these are going to use. So it depends on how scalable is it going to be. Would also depend on something else. You think of these two structures. Okay, yep, so how much storage do we have? Yeah, again, so that's part of the scalability, right? We need, our storage is rapidly going to increase, so NoSQL is a good choice. What about complexity? Right, so here we're tending to work with a simpler data model. For example, I don't think we'd want to run Amazon or Blackboard off a NoSQL database because the data model's too complex. There's dozens and dozens of tables and relationships, and we probably need that well structured, right? When we have a student in Blackboard, we need certain information about every kind of student, right? It's gotta be well structured and organized. Something like a mobile app, typically the degree of complexity and the things we're asking you and the types of data we have are usually simpler. So it's lots and lots and lots of simple data. So in that case, NoSQL is a great option. It scales, it's faster, it's lightweight, but it doesn't have some of the structure and organization of a relational database. So there isn't a right and a wrong, but more and more mobile apps are moving towards this kind of a structure back end for these reasons. I know my font's getting smaller and smaller. Okay, so for those of you who had question number 3, if we're going to exchange data between 2 different applications, there's basically 2 standard formats. What are they? And which one's more popular and why? Okay. Which one is more popular and why? JSON is definitely more popular. How come? So traditionally, probably 10 years ago, XML was industry standard. So we could have 2 entirely different applications built on different technology platforms. Over here, maybe we had a Java application connected to an Oracle database, and we wanted to exchange information with an ASP.NET web application with a Microsoft SQL Server database. And those 2 applications needed to talk to each other and exchange some data. So 10 years ago, XML would have been the format. XML is still around, but we're using it less and less. We're using JSON more and more. Do I have a comparison here? Yeah. So here, for example, is the exact same rendering of a document, an XML document and a JSON document. So they both represent the exact same data. And many applications would be able to read or write either one of these. So what is it that makes this one faster and more lightweight? Something you can actually see. Yeah, it has less characters. Why does the JSON document have less characters than the XML document? One very simple reason. Yeah, in an XML document, every node is repeated. It's got to be open and it's got to be closed. Well, this isn't a big document. What if there's 10,000 employees and we're trying to send this data from one application to another? Suddenly, this becomes much slower. It also uses up a lot more bandwidth, which factors into hosting costs and things like that. Also, without the closing tags and with the spacing, the JSON is simply easier to read. Okay, so if we're looking at the file, it's easier to see it and understand what the data is. One of the other nice things about JSON is when we're working with one of these NoSQL databases, many of the databases themselves store the data as JSON. Very grand. So if our data is actually stored in JSON format in our database, it's super easy for our app to pull data out or send data in. And also really easy for any 2 applications to talk to each other. We'll talk a bit more about this later on in the class. Can you think of any examples? What would be a simple example you can think of, one that you've maybe used as an end user, where you've got 2 applications that talk to each other and exchange some kind of data? We do it all the time. What would an example be? Okay, so a multiplayer game, yep. So that would be 2 instances of probably the same application. What about when we have different applications? Why would they ever need to talk to each other? Absolutely, right? A third-party authentication, right? That's all transmitted using, guess what? Right? Your credentials credentials are transmitted to Google's login service. It validates and it sends back a response. Either, yes, this user's authenticated, and by the way, here's their Google profile and all of their friends and their shopping habits and everything else, their search history, or it sends back a no, not authenticated. What else would be a common use where you see two applications talking together? Probably using one of these two to exchange information. We do it all the time in the apps we use every day, both online or on our mobile devices. Okay, like an intent within an Android activity to launch something else. Yep. Okay. And there, we're invoking another activity, and we may or may not be passing it data. Right? We might be passing the phone dialer a phone number, for example. Yep. Any other examples you can think of where we're using one application and it's making a call or talking to another application? Okay, how does WhatsApp do it?
There are two different profiles and we can actually do that. There are two instances of the same thing.
Yep.
She has installed on her phone and I
Yep, you can communicate together that way. Yep. What about, I'm thinking more about two separate applications. Yep. Okay. So how do those communicate together? Okay. Right. So yep, and you can do that in one app. Yep. That works. What happens every time you go to buy something online? When you go to pay, either through a mobile app or on a web application? Right, that payment gateway. So you put in your credit card number, right? The app itself or the site itself, they don't have the ability to validate your credit card. Who validates the credit card? A payment gateway service. Moneris, Authorize.net, VeriSign, one of those. So what they do is they take your credit card, your information, either in XML or in JSON, and it sends a request to that service, which validates the card and sends back some kind of response, right? Payment okay, not enough room on card, invalid expiry date, whatever. So the request and response comes in one of these two formats. What if we're shopping and we want to know how much it's going to cost to ship something? Where do you think that shipping rate comes from? Yeah, so all of the shipping services or the post offices, they have services where they say, tell us where the item's coming from, where it's going to, and what it is. Right, how big is it? You send us that information and we'll send you back a list of shipping options with delivery times and prices so the user can choose. The store themselves where you're shopping, they don't come up with those shipping prices. They're sending your info to a shipping service and it will return that data to you. So most of the apps we use every day, they're not just the native core functionality, they're extended by calling out to other services. And in order to make this happen, we need some way to move the data back and forth. So typically that's JSON. We'll actually look at one example of a service later where we can call it and we can specify whether we're going to send it, we want to use XML or whether we want to use JSON. So we'll come back to this a bit later. So JSON, I've just made that one bold because it's now the standard. Okay. And if you had a number 4, what is a REST API? Don't just read me the definition from Wikipedia. Let's put it in words that you could go home and tell your roommate who's not in this class what a REST API is in a way they would understand. Okay, so yeah, it is modular code. Yeah, that's part of it. Obviously, it's more than that. It's modular code that does what? All the examples we just talked about use REST APIs. So it's a service we want to, and so there's two sides to it. So if we built an online store and we want to let our customers look up a shipping rate or get their credit card authorized, are we in that case, are we creating an API or are we consuming an API in those examples?
Embed that API in our.
Right, so are we creating it or consuming it in those examples? Yeah, we're consuming it. So we didn't build the API. The API is a modular code library created by Canada Post or UPS or Moneris for checking credit cards. And they allow us to call their code library. We send it data and it sends us some kind of response back. So typically, we look to extend our functionality. Hey, there's some piece of functionality would be really nice to have in our app, like letting somebody sign in with their Facebook or Google account. We could write that code ourselves, but wouldn't it be much easier to just find the API that does it? Read the documentation. How do we work with this API? We'll call the API and we see what we get back. So it's a really inexpensive, often free way for us to extend the functionality of our apps because other services make APIs available. Now that's one example. So typically that's where we start, is consuming other APIs. But there's times where we want to write our own APIs. Why would we ever create an API within our own application? Exactly, right? So that, let's say we built a game app and our app either on disk, in local storage, or in a cloud database, right? We store the user scores. Some other game library wants to be able to access how is somebody doing, and I want to see their scores. So we can write an API that would expose some, in a modular way, expose some code so another application could access only what we allow them to access within our own app. So typically, they would make a JSON or XML call to our API, we would send them back some data, and that application could do whatever they want with the data. So let's take a look at a common one. So whenever on either end of an API, we're going to need documentation, right? Because either it's a service some other developers wrote that we want to interact with, or it's a service we wrote that other developers want to interact with. So in either case, having the documentation to this is key. Because otherwise, how do we know what functions are available? How do we call them and what do we get? What do we send in and what comes back to us? So here's Spotify's API, right? So we can see all of the things we can do. So for example, if we want to get a specific album, a list of albums, or all of the songs on one album, we would make a call within our application to, here, let's go get all the albums. So it gives us a URL. So that's part of the REST API. It's HTTP based. So every method we want to call has a URI, a universal resource indicator. This method runs at this address. We can call it from a web page. We can call it from a desktop tool. We can call it from within our own mobile app. If maybe we want to be able to display somebody's, if we have access to their Spotify, if they can authenticate through Spotify, we can then access their Spotify albums and playlists in our app through the API. Right? So it tells us, well, you need authorization. You can't just go in and get any album. We need to have an account. And here's what we send in, right? We need a Spotify ID. And what we get back is a JSON object and it shows us the full documentation as well as an example. This is what this API method returns. So we're going to get this big JSON object. And you notice it's one object, kind of like our NoSQL database. There's no relations. Things are just nested. So one album, there's information about the album itself. And then when there's nested, so this album is available in this market, it's just an array. In here. So one object gives us everything to do with this album. So we'll come back to APIs a bit later on in today's class. We'll play around with a few of these. Okay. So you guys basically named all the stuff I wanted you to name when I asked you those questions. That's good. In fact, you did more than I. This was my note, and these were your answers. So I'm going to talk a bit more about NoSQL. We'll take a break in about 5 minutes. We come back, we'll actually download probably the most popular NoSQL database. We can play around with it. So you can see how that works and how it's different from the kinds of relational databases that you're used to using. So you guys mentioned the big motivation for NoSQL database, which was scale, right? You mentioned it as well in the green. So the idea with relational databases is we would often come in large application, we'd come across storage limits, right? So what's the solution? We have a relational database server. Let's say we're running an Oracle database or an SQL Server database, and we use up all the memory on that machine. We've built a big application. We have lots of users. There's new data going in. So what do we have to do at that point when that machine capacity basically is full? What's our only choice to keep that application running? What do you do when your database fills up? Sorry? You purchase more storage. Yeah, well, this is kind of before cloud came along. What would you do if your database filled up and your server was totally full? Maybe you can't delete. If you could delete, sure, but maybe you can't. So what would you have to do? You've already done that. These are good suggestions. But we're paying a database administrator $90,000 a year, so they've already done that part. Yeah, we get another server. And we get another license for our SQL Server, our Oracle database, and we put all the security on it and all the patches. We replicate the server. How much do you think that costs? In the tens of thousands of dollars, right, for each server. So it became incredibly expensive for popular applications to keep up with the storage demands. They're constantly adding new hardware, new software, new licenses, patching. It became too expensive to manage. So yes, we had cloud. Somebody over here mentioned cloud, which takes care of part of the scaling, but then even within the database structure itself, we wanted something that scales. There are two other challenges with relational databases. The first one is if we're using a database like Oracle or SQL Server, right, the data is stored in some kind of native format. Oracle has its own format, SQL Server, DB2, they all have their own formats. So whenever we want to work in our application code, we want to work to that database, there has to be some kind of translation between our application and the database, right? We write an Android app in Java, it's saving data to an Oracle database. There's overhead, there's performance and work that goes on to take an object, to take a record or a query object out of an Oracle table, and then convert that into, say, a Java class. That takes time and it takes work. And that process, some of you have probably heard of, that's called object relational mapping, and there's tools for doing it. So for example, in the Microsoft world, we've got the entity framework, which is an object relationship mapper. It converts database objects to business classes. But there's a lot of work involved and a lot of design. The other problem with this is this one. If you think about our database schema, it's kind of like the drawings for a building. Right? Before we go and build and put shovels in the ground, we're going to build a new building. We plan it out and we draw where everything is. And that's fine. The challenge becomes what happens once that building is built and now we need to make changes to it. Right? Sometimes that can mean tearing it down to redo the foundation. So has anybody ever had experience with this? You have a working application and then you have to go and change your database later. Anybody ever had to do that? What was that experience like?
So it was like we have to change the primary keys. So in a situation, so the situation happened while I was working in SAP technology. So at that point of time, we had to downgrade the system and move to another version of it. So it did have a business impact for a little bit of time.
Okay, so and that's that's a pretty common scenario. We may have downtime and we have a lot of work to redo the structure of something when we have an application sitting on top of it. So this structure is not really designed for scalability, not only in terms of amount of data, but in terms of the evolution of the database. And if our applications are successful, the databases are going to evolve. Because if we're doing this well and people are using it and our app is making money, then suddenly we're going to want the product owners are going to want other things. And that often involves changes to the database. So one of the beauties of this structure is there is no schema. So let's say today we say for a customer, all we want is a first name, a last name, and a cell phone number. Right? That's all the information we're capturing here in our ordering. Maybe in a few years, all devices, I mean, it's obviously coming, but every device is going to have a working thumb scanner or eye scanner. So instead of a username and password, we just want to be able to add in either an iris scan or a thumb scan. Here we'd have to go in and add a new column, add it to our business class, and potentially rewrite a lot of our code. Here, no problem. So I have an old customer account with just first name, last name. I can just add in a field for an iris scan. And if I don't have one, no problem. If I have a thumb scan, I can add that in. So this is designed to be flexible. We expect that structure is going to change. And it's much, much less work to do this in a schemaless database than it is here. So it's really a different way of thinking about how we store and structure and manage our data. And it's kind of weird when you get started with it. You think, oh, I shouldn't be allowed to do that, right? If whoever taught me relational databases saw me doing this, they would not be happy. And we're really kind of breaking a lot of the rules. I won't read all this to you. So again, we're basically working with documents, and JSON is really just keys and values. If we just go and look at back to our JSON sample, right? We have a key and we have a value. This is all our database looks like. It's easy to look at, easy to read, fast and flexible. And it's definitely designed with speed and scalability in mind. So it's not right for everything, but where our app needs to be fast and we're going to have a lot of data, and that data is going to grow exponentially. We're probably going to want to store it in the cloud. This is a good choice. So we don't do things like foreign keys. We don't have complicated SQL queries or joins. If we have a whole bunch of related data, we just stick it together. We just nest it inside of a single document. And there's cloud services readily available for us to take advantage of this. We're going to sign up for a free one and play around with it. shortly. All right, it's I missed by 2 minutes. That was pretty good. Any questions before we take a break? Okay, let's take a 10-minute break here. We'll come back just after 1 o'clock.